Okay, I think it's our November 8th, the Wednesday, today on a week 12 of our semester. And it's time for us to have a look again of what we're covering this week on this course. I'm also recording this session so that anyone who wants to watch it asynchronously can do so. But as always, I just want to make really certain that you know that even if you're unable to join at these very specific times when I've set these additional optional review sessions, don't feel that you don't have access to me in a synchronous manner as well. I'm always happy to schedule one-on-one times with you. Just let me know. I've also tried this and last week a little bit of a new format of adding those discussion forums to our weekly learning modules. So we'll see how those work, if that's something that's worthwhile for us to pursue further. Um, this week really marks us moving to a kind of a new whole bigger of a unit. So far, we've covered quite a lot of material. We started with some basics. We had a look of the skin. We talked about bones, skeletal system, and we talked about muscles, muscle tissues, and also those great muscles, skeletal muscles that we use to create movement in the body. The really rest of the semester for us is dedicated to probably one of the, if not the most important systems in the body, and that's going to be our nervous system. This week is simply us kind of getting our bearings, having a big, uh, large strokes overview of what to expect, what to think in terms of the introduction to nervous system, what themes will come up, and then throughout the rest of the weeks that we have for this semester, we'll dive into more detail of each of these separate areas. In terms of just kind of getting a plan for today, I wanted to start with just a few words of kind of putting everything into perspective, where we are in a bigger picture of the whole semester. I also wanted to mention really quickly one of the projects that I've been working on and one of the themes that's really near and dear to me. And I'll be sharing more information about that, but I wanted to put the plug out there today regarding the World Kindness Day that's coming next week. And we have a whole week of events at the college regarding that. We'll spend most of our time looking at the introduction to nervous system in terms of I want to make sure that we have a clear idea of the plan for the week, what sort of assignments I'm looking for you to do and as a homework this week. And then we'll spend a little bit of time reviewing the key takeaway messages from this week's chapter. We'll wrap up if we have time looking a little bit of the homework as well. And as always, I try to make sure that we have that time for the questions. I do want to start, though, even before I jump to that kind of putting things in perspective, with a really quick notion that if for some reason you would have missed an exam or practical or both last week when we were working on those, you should have probably received, or you will be receiving very briefly from me, a message, kind of just checking on where you are. And the reason why I want to do that is because these assignments are worth so many points that it's important for me to know that you're not falling behind, you're not struggling to get that final grade that you want to. In my classes, really, communication is the key since we're not meeting multiple times a week face to face. If you let me know what's going on, I normally am able to help out. So please, please, please consider of reaching out to me. I'll also try to reach out to you actively, but it really, really helps if you let me know where I can help you, where we're doing. So that's just a note for anyone who missed those. For everyone who were able to submit their exam too and their practical too, I am so incredibly proud of you. You really have done, I'd say, about 2/3 of this class for sure, if not even a little more at this stage. Really, the key and secret to great success in these classes is the continuity, submitting those works, collecting those points, and getting where you want to be with your grade. So finish line is at the side. So let's finish up strong. Let's get you that grade that you want and see where it takes us. Um, this slide is just kind of to give us a little bit of an idea. It really outlines everything we have covered and will cover this week. I think I used a very similar slide at the beginning of the semester when we were looking what to expect. So far we've covered the two big units, the first exam which covered these really basic introduction, getting us to the same place in terms of the basic concepts, integumentary system, skin and associated structures, and the intro to bone and cartilages. Then we took our first exam and we moved on to look at themes such as your skeletal system, different bones in your body. We talked a little bit about joints. We talked about the muscle tissue and the big skeletal muscles that create movement in our body. Then last week we took our second set of exam and practical, and this week we're really focusing on this introduction to nervous system. Never mind about that central nervous system that I've highlighted there. I sometimes teach this class in an 8-week format, so I think it's a remnant from that. But we will cover for the rest of the semester different components of the nervous system. Looking each week into more detail of each of these. This week really is just getting us kind of set and getting us an idea of what to expect when it comes to the nervous system. We'll cover some important concepts though, so there's definitely learning happening this week. Before I move any further, two things that I want to take care of, and I'll just change this just so that no one's confused. Sometimes I know that there's a lot going on and students look at the videos and not always with the sound, so I just want to make sure that no one's confused what's going on. And let's have a look of the next slide, which is really all about the next week, one of the kind of additional things that we've got going on as a college. So next Monday, I believe, which is going to be the 13th, marks actually World Kindness Day. And the reason why I think it's kind of a big deal is that you might have noticed that I've incorporated on this course throughout the semester things that are a little bit aligned with self-care, kindness, kind of goal setting, management of own goals. So that all work is something that a lot of my face-to-face students do. But I think it's important that we also, on a level of a whole institution, take a little bit of time to appreciate what's happening in the world. And the World Kindness Day is a big initiative that I really do support, and I think that there's so much that can be done. We kick off our World Kindness Day on this college on Williams campus, where actually my office is located. We have a whole day of very, very exciting and very interesting things going on. For example, we will have a food truck. So free food, that's always a bonus. We will have also all kinds of swag. I saw we were working on things like t-shirts, which is incredibly exciting to have those. Our kindness crew t-shirts for anyone who's enthusiastic about being part of that. Other swag. And we actually have a really cool idea of a table where you can take what you need and leave what you don't. So exchange things such as clothing, but there's going to be other stuff as well. I'll be posting an announcement about this in just a little bit on our Canvas course announcement. So keep an eye on that. If you do end up taking part on anything like this a day, uh, take a selfie while you're there and upload it as an extra credit assignment on our course, and I'll be sure to recognize that with the points that count towards your final. Having said all of this, I do want to make sure that I'm communicating correctly. The World Kindness Day is not all we're doing. We're actually having kindness spread around the college for the entire week. Next week, and we have multiple events throughout the week also at the Pecos campus. So we'll just kick it all off at the Williams, but I encourage you to join wherever and whenever it's convenient for you. It's not a requirement by any means, but if that's something that you are interested, by all means, consider taking part. On the theme of kind of kindness and self-reflection and all that, one of the things I've been working on has been using this book by Young Pueblo, where we've been looking every week at just a random quote and kind of reflected on that very briefly before getting into the actual learning material. So just because I kind of anticipated that it might be a little bit of a one-man show here today, that I don't have a synchronous attendance, which is totally okay, I picked up one random page, and what I landed with was a thought and a quote from Young Pueblo where he says that I closed my eyes to look inward and found a universe waiting to be explored. And this really resonated with me, and I thought that how convenient it is for a week when we are really talking about nervous system, because really nervous system is one of the systems that I think really is where we are housed, where our experiences happen, where our interaction with the rest of the world happens, where our dreams, hopes live. It's all a creation of your nervous system. Obviously, we have the physical body, but the physical body itself doesn't create those experiences. A lot of those experiences happen at the level of the nervous system, especially at the brain, at the central nervous system. So, really, we ought to explore a little bit of this amazing universe that we've got inside us. So on that note, the next picture that I have is one from one of the exhibitions that I really, really personally enjoyed. And what we're seeing here is essentially your nervous system. We're seeing your brain and we're seeing your spinal cord, which form our central nervous system. And we're seeing a bunch of other nerves throughout your body. These are some of the bigger nerves. Obviously, we're going to have smaller to the scale of microscopic ones. But one way how I've spoken about nervous system in the past to my students, which I still think kind of resonates with me, is that if you look at this picture and if you think about it, this is all you are. And everything else is going to be just casing and supporting structures for your body. So everything else is where you're packaged at and what tries to preserve what we've got going on here. But you and your experience of you, your experience of the world, all that happens at the level of a brain. So I think that that's kind of a exciting thought and exciting way to look at it. So really tying into that what we saw from the young Pueblo. Moving onwards, let's have a look at what are our goals for this week. This week, we do want to make sure that we complete 2 assignments. I have a chapter quiz for you, and I also have a practice anatomy activity for you. So you'll be answering quiz questions, but you'll be also able to practice those anatomical structures. Both are due at the end of the week, so you have until end of the week to work on those. And as always, if you have missed any assignments, please message me. I'm always happy to work with you. Make sure that you get those points collected. So that's the plan for this week. That's what I'm looking for. And I think that on that note, we're ready to start looking at the chapter material, looking at the material that we have for this week's lecture. And please remember that I have a full set of lecture videos for you on Canvas. Those do go into a little bit more detail. What I provide during these review sessions is really the nutshell version of the story. So, and I kind of tend to update and add more stuff on those full-on lecture videos. So please consider referring to those on the Canvas. So what we're seeing here, I wanted to start with two concepts that really were eye-opening, at least to me, in understanding how complex and how fascinating and how exciting nervous system is. So I think that one way to look at it is that the brain is really the most complex organ that you have in your body. I was very lucky that in addition to pure medicine, pure anatomy, I've been studying also psychology and neuroscience during my time in education as a student. And I really think that brain is where it's at. Brain is something that we don't fully understand yet, but that's everything that you'll ever experience happening there. I ended up actually going and building a career looking at the heart, which I think is the second most exciting organ in our body after the brain. So what I've got here is a reference to a book that's one of my favorite books when it comes to this topic, written by a neurologist known as Oliver Sacks. In this book, he kind of explores different kinds of case histories of some of his patients. And one of the stories which gave the title for this book is about a patient that he refers as Dr. P. It's fairly common for us in psychology that we use the initials of the patient when we're doing records so that we don't share private information. But Dr. P, a highly educated man, but he suffered from a condition known as visual agnosia. In visual agnosia, the patient actually sees everything correctly. There's nothing wrong with the eyes. They're seeing what's in front of them, but really that process of giving meaning to what's being seen, which happens at the level of the brain, is impacted. So there's really impaired recognition of visually presented objects. And that's what happened with Dr. P. And one of the examples of the objects that he didn't recognize was that whenever he saw his wife, he thought that he was looking at the hat. And this creates in this story rather interesting situations. For example, regarding the fact that he's going to try to put what he perceives as a hat on a shelf out of the way, and his wife, who he's actually trying to put away, is obviously going to object to that. She's not going to be very happy of his perception of her. So it shows to me really how fascinating brain is. Through things, when things go wrong, we have been able to gain a lot of understanding of what's normal. In case of Dr. P, this was occipital lobe damage and also some temporal lobe damage. So through disorders, we've been able to localize functions and localize processes into different parts of the brain. So we learn a lot from when things don't go right about what happens when things do work out correctly. So a fascinating read if you're looking for something to keep you occupied. I definitely recommend this book by Oliver Sacks. Another case that I wanted to talk about is a fairly famous one. I think a lot of my students have heard about Phineas Gage. Phineas Gage was an American railroad construction foreman. And back at that days, a lot of the railroad work involved removing large parts of rocks and large masses of stone out of the way. And how you dealt with that was to work with black powder. And you drill a hole, fill that hole with to the rock, fill that hole in the rock with black powder, compact it, and then explode. And that way you're able to break apart those rocks much more effectively. Interestingly, though, at the time, this was very manual labor. And as part of the process, when you have that bore, when you have that opening on the rock, you need to compact the black powder in there. And to do that, he was using a large iron rod. And I think that he's holding that in that picture that we're seeing on the screen. And one of the unfortunate things that happens when you have metal objects and stone or rock, sometimes you can unintentionally create spark, and that's exactly what happened. The black powder that he was compacting onto this opening actually ended up exploding, pushing out that metal rod through his head and destroying the left frontal cortex of left frontal lobe actually of the brain. And this damage to his left frontal lobe was pretty extensive, but interestingly enough, Phineas survived this and he lived for another 12 years. And in this picture, you can see some of that damage that was caused. But what's interesting is that even though he lived through this, people who knew him said that his personality and his behavior changed completely. So he was no longer this joking, mellow guy that people have came to go. No, he was much more irritated, much more impulsive, much more unpredictable. So that leads us again to understand that your frontal lobes play important role when it comes to your personality. Also things like executive functions, planning, dreams, hopes, things like that. So through this damage that Phineas experienced, we were able to gain a lot of information about what happens normally on this area. And we see that the frontal lobe is really, really important for one's personality. So I think that those were two fun stories to kind of get us oriented. Let's have a look of what's going on with the nervous system and what is nervous system. Well, nervous system really is, I like to explain it to my students, it's a communication system and it's also a control system, but communication system that we see in our body. There's a strong connection between endocrine system and nervous system. And we will actually start our BIO202 course. That is the next course on this sequence of courses that you're taking after this course by talking about endocrine system. And we'll see that that's all about hormones. And hormones is the second control and communication system in your body. And now, for the rest of this semester, we're focusing on nervous system. So there's some similarities with endocrine system and with the nervous system, but there's also some big differences. And I'm going to leave that discussion for once we get to the endocrine system. I think that this time we're just going to focus on the nervous system. But remember, it is a system that plays an important role in controlling your body processes and communication between different parts of the body. And what we end up seeing is that nervous system responses are very, very fast and very specific. So we will see a concept known as action potential. These are electrical impulses that pass through the nerves, and these are very, very fast. We're talking of milliseconds for passing a message from one part of the body to another part through the nervous system. And it's also very specific. These messages only travel between two body parts. They don't travel randomly throughout body. They're very, very targeted. And what we end up seeing is that we see almost immediate responses through the nervous system, kind of contrasting to that endocrine system. That's not the case with the most hormones. Um, what else can we see about nervous system? Well, I think another way to think of nervous system is to really divide it into three different parts based on the processes that we have going on in there. So let's have a look of that. These three parts are all interconnected, but yet separate. So we have, as the functions of the nervous system, the function of collecting sensory input. So we're gathering information via our sensory organs. And this doesn't only have to be external information, it could be also information about internal body states. But we have sensory organs that collect the information, convert that information into electrical impulses that then travel in your nervous system. And those impulses reach your central nervous system and especially your brain, which is really the integration center where we process and give meanings to this information. Before this stage, everything that our sensory organs perceive and pass as messages are just electrical impulses. They themselves are not a perception. The perception, the meaning for these impulses is assigned at the level of the brain, at this integration center. There are certain times when that integration doesn't happen at the brain. It can happen also at the level of spinal cord in terms of reflex responses and so on. But most of the time, it is going to be the brain. And finally, the last part of the functions of the nervous system have to do with the motor output. So this is where we have various different kinds of effectors. I've highlighted on this picture as an example of a skeletal muscle because it's kind of an obvious one, easy. You create a movement in response to what you sense. But this could be other things than just muscles. It could be, for example, glands, that we activate certain glands in response to things that we are perceiving. Let's say that we're getting too warm, we start sweating in response to that. That would be a good example. So again, we're sending out simply just electrical impulses, but those electrical impulses can be converted into meaningful output, which again, to me, is a kind of a amazing thing about the body, that we're not just sending these electrical signals, we're actually getting actual things, meaning out of those. I have another illustration that I kind of tried to do to simplify this concept, and this might bring you to remember the concept of homeostasis that we've discussed about before. So you remember how I said that homeostasis is one of the core concepts that I want you to be extremely familiar with and that we'll keep repeating time and time again. So we're doing just that here. We're seeing, you remember, homeostasis referred to maintenance of the consistent internal environment, and that often happened through that homeostatic feedback mechanism loop, which we're seeing here. So stimulus is something that's changing. The change is picked up by sensors, by our detectors. This is usually our sensory organs, sensory structures that pass that message to the control center, which was usually the brain, where we give a meaning to that information. We typically have a set point, the acceptable range of values for this stimulus that we see. And if we fall anywhere outside the set point, then we recruit an effector. And most of the time in the body, the effectors aim to stop the stimulus from happening. And these effector responses can be very, very different. They can be anything from behavioral responses to physiological changes in your body. But the ultimate goal is typically to stop the stimulus from happening. So we're seeing negative feedback happening. There are sometimes times when we want to with the effector to make the stimulus happen more. But there were only 3 examples of that we saw. We had our childbirth, lactation, and blood clotting scab formation that we saw. But at all other times, we're doing negative feedback. We're stopping the stimulus from happening. These positive feedback responses were kind of rare. So I think that that's a good kind of an overview of the main ideas that I want you to take away about the functions of the nervous system. And what I wanted to do next, I wanted to kind of set our sights on forming this kind of a bigger, broad idea of all things that we might be discussing as we are tackling nervous system during the remaining weeks of our semester. So this is an overhaul, a large, high level view of what we'll be doing, and then we'll get to dive into different components of the nervous system in greater detail later on throughout this semester. So nervous system can be divided into 2 parts. It can be divided into central nervous system. Central nervous system is made by your brain and also by your spinal cord. So your brain and spinal cord together are kind of I would describe it almost as the computing and processing part of your nervous system. Um, Typically, central nervous system is located, especially in humans, but also in many animals, on the dorsal side of the body. So the back side of the body, you see, you have your brain, you have your spinal cord running at the back. We're seeing that integration and that control happens there. Let's have a look of next our peripheral nervous system. Peripheral nervous system is located outside the central nervous system. So this is all these nerves throughout our body and also various different sensory organs that we have. One way to think about them is almost as these communication lines, whether they're antennas that send messages or receivers that collect messages. But they're located outside the central nervous system. They include, for example, our spinal nerves that we're seeing on this diagram, also our cranial nerves. So really, really important parts. What I wanted to do was to also show another kind of way to divide the nervous system. We can talk about our sensory and motor branches. I think that we saw this a little bit earlier when we talked about, but we can kind of give another name for these. So these sensory divisions of the nervous system are known as afferent. And what I mean when I use the term afferent is that I mean that they carry messages towards the central nervous system. So I always do little simple mnemonics. I think of afferent is like arriving. So messages in sensory system are afferent messages. They're traveling towards your central nervous system. We also have our motor branch, which deals with efferent messages. Efferent messages are messages that are leaving from central system and traveling away from it, typically to the effector organs, to the organs that were responsible for acting, causing those changes in our body. Again, we can do a bunch of other divisions in this motor branch, in these efferent branches, but consider it as messages away from the central nervous system. So in my mind, I would use a mnemonic as exiting. So efferent for exiting, going away from the central nervous system. Now that we've had a look of that, I think that what I want to do next is kind of just summarize what we just learned and make a little bit of a kind of a sketch so that we have an idea of the key concepts that we just discussed. I'm sure you caught those, but we know from learning, we know from the process of studying that repetition is really big part of that. So we can take our nervous system and we can divide our nervous system really into two branches. There's two parts that when it comes to the nervous system that we end up seeing. So let's do that division first based on everything that we have learned so far. Nervous system, we are going to divide that into two branches. And just let me remove that one line that jumped out there so that we're keeping a little bit tidier notes. Last time I tried to do these drawings on a paper, I think that that was a little laborsome. So let's try to do it electronically and see where we end up with. And the first branch that we saw and we just talked about was our central nervous system. So central nervous system as a part of the nervous system was the part that contained our brain, and it also contained our spinal cord. And if we think about central nervous system, I think that it becomes obvious to us that these structures are really, really important when we think of the anatomy. They're really well preserved in our body structures. If you think of the brain, for example, it's inside skull, this bony casing. So we're really putting great effort on protecting these parts. Same goes for the spinal cord. If you think about it, it's running within the vertebral column, protected there. So central nervous system being an important structure that we want to make sure that we're protecting it. And you remember that that was typically located always at our dorsal portion of the body, so at the back of our body. So that's something to note about the central nervous system. The other branch of the nervous system was our peripheral nervous system. So let's add that as well to our listing of the structures or portions of the nervous system that we're seeing. So our peripheral nervous system. And this was really all the parts that are not part of the central nervous system. And again, let me just tidy up my notes a little bit. What we're seeing with the peripheral nervous system is that this was what I think students in layman's language often think of as the nerves. So these nervous system tissues that carried messages from one part to another. We would also include within the peripheral nervous system our sensory organs as well. And I'm just going to abbreviate it in terms of the saving time here. So we see our sensory organs as well as an important part of the peripheral nervous system. So let's add that to our listing here that we're seeing. And if we thought about the our peripheral nervous system, I already mentioned this, but just to highlight that this was the portion that was located outside the central nervous system. So all the parts that are part of the nervous system that are not either brain or are not our spinal cord. Another division that we're going to see as the next concept that I want to talk about, but I'm going to do the division already now, is a division into somatic and autonomic nervous system. So we can do this division as well. So let's add our somatic and our autonomic nervous system. And we will get to talk in great detail about each of these different portions as we move through our lecture material for the remaining of the semester. But I think it's really useful to have kind of this broad strokes division or broad strokes graph to have an idea of different portions of the nervous system that you can think about. So let's talk a little bit more about the autonomic nervous system. Autonomic nervous system then again can be divided even further into two branches. So autonomic nervous system responses, as the name proposes, happen automatically. We don't really think about those. Those are things that are not under our voluntary control. Those changes just happen, and we can do a division into two separate branches within the autonomic nervous system. So let's list those as well. So we're going to see that we have our sympathetic nervous system branch. And we also have our parasympathetic branch of the autonomic nervous system. And you might be at this point wondering that, well, what is this sympathetic and what is this parasympathetic branch? What do I need to know about those and why do I care about those? And I think that that might be a good next place for us for our review of the kind of oversight of the nervous system to pay a little bit of attention. So let's do just that now that we have this general appreciation of different parts of nervous system, and let's have a look of what we can learn about the differences between the sympathetic and parasympathetic nervous system. And a lot of the time you end up hearing in layman's language that sympathetic nervous system is described almost as this fight or flight response branch of your nervous system. So this branch of nervous system, automatic nervous system, is autonomic nervous system is activated when you're dealing with things like excitement, fear, anger, embarrassment. So physiological responses that are associated with the activation of the sympathetic nervous system includes things like your heart rate going up, your blood pressure going up, getting elevated, your respiratory system, especially the bronchi, the tubes that carry the air to the lungs, they tend to dilate in response of making sure that more air can get into your lungs. We're also seeing dilation of the blood vessels when sympathetic nervous system is active. So we're ensuring that we can carry a lot of blood to the muscles, whether it is that you physically engage into preserve self-preservation by fighting against the danger, or you're trying to flee from the danger, from that challenging situation. One system that I can think of, or two systems that I can think of that are not terribly activated while the sympathetic nervous system is active, are going to be our digestive and urinary systems. So we're not really worried about converting food that you've consumed into energy and storing that energy when your life is at danger. So when sympathetic nervous system is activated, you're dealing with very immediate risk and immediate responses to that. So digestive system typically tends to get depressed, less active during the activation of the sympathetic nervous system. Same goes for urination and urinary system. You're not really needing to worry about peeing. You're needing to worry about survival, not about the long-term importance of urination. Is that parasympathetic nervous system? I often describe that if you considered that sympathetic nervous system was that you were facing some kind of a danger or threat. So you were fighting for your survival or you're trying to escape that situation. Parasympathetic nervous system is more of a, I compare it to how you feel after Thanksgiving meal. So this is the rest and digest branch. This is the branch that is active when you're not really engaged into a physical activity, when your body is about the maintenance and preservation mechanisms. So your pupils typically end up constricting, your heart rate and blood pressure decrease, your respiratory system, the bronchi typically end up constricting. Blood is actually directed not to all other parts of the body, but mainly to the digestive system and urinary system. This can sometimes also cause why people feel chilly when their parasympathetic nervous system is activated. You literally are directing the blood to those maintenance functions. So we see, for example, our digestive system acting particularly actively during activation of parasympathetic system. Your saliva production typically is also elevated. Things like production of the urine, urinary system is highly active again during the activation of parasympathetic nervous system, and you are doing things like producing feces and so on. So this is really the rest and digest, where you're processing things in your body, directing energy resources to those long-term mechanisms, long-term maintenance, if you wish. So what I wanted to do next was to kind of shift gears a little bit. We have this broad strokes general understanding of the nervous system. We did a diagram that looked a little bit like this on our previous slide. And I want to shift our attention to talk a little bit about more of a microscopic, smaller level scale of nervous system. And we're going to talk about a structure known as our neuron. So neurons are nerve cells, and in reality, neurons are a broad group of different kinds of cells, very varied group of cells. So we typically teach you this overly generalized model of a nerve cell, but in reality, it's much more varied range and group of structures. So I'm just trying to give you a very simplistic representation that applies to most nerve cells, but remember that there's going to be much more variation that we see. And when we're talking about nerve cells, one of the things that we end up seeing is that we can actually measure nerve cells in your body as well. So we will get to talk about that. And I think that what we're going to do, we're going to spend a little bit of time talking about these different parts of the nerve cell. But before we do, I want to explain why we're doing that. What we can do, we can actually put an electrode inside a nerve cell, inside this long part of a nerve cell, and measure electrical charges in there in comparison to the area outside the nerve cell. And we can see that there's changes in electrical charges along the nerve cell as messages pass through it. So one way how some of my students like to think of this is to think of nerve cells almost like electrical wires. They're not electrical wires, they're living things They're living structures, but they pass electrical messages from one part to another. And this passing of an electrical message can be perceived with measuring equipment. This measuring equipment would be very, very highly advanced microscopic structures, microscopic electrodes that we would put just inside this tube, inside this part of the nerve cell that we're seeing, and measuring the charges inside there compared to the outside. So let's have a look of a neuron, a single neuron, a little bit more before we start talking about these electrical charges in more detail and what happens with them. I think that that's going to be useful for us to gain a general appreciation of what a nerve cell looks like. And we can sketch that together again. I think that that's always a good place for us to start. So let's start by sketching what an average nerve cell would look like. And like I said, remember that there's many different kinds of nerve cells. So I'm just drawing one generalization. In reality, there's far more variation, far more adaptations than what I'm showing here. But nerve cell has a cell body. Like any other cell, a nerve cell as well is going to have nucleus. And this is going to be important for the control of the processes that we see within the nerve cell. So the nucleus plays important role in doing things like regulating, summating up that are we going to pass an action potential or are we not? And I know that for some reason my technology here is giving us a little bit of a headache. So let me try to remove some of these additional lines that just appear when I try to do a normal drawing. So we're seeing that cell body that I talked to you about, and we're seeing a nucleus within that cell body. So that's what I'm really trying to show here. One thing that you might notice really quickly, and let's label that cell body. I think that that's going to be useful for us as well. And again, let me just tidy up our diagram a little bit. So we're going to add our cell body. And like I said, the cell body will include also the nucleus. So that's what we're seeing there. This cell body will have structures that kind of reach out from there. And these structures, one way to think about them, a student of mine described them to me as them thinking of them as little antennas that are constantly collecting information from the world around this neuron. So we're constantly gaining that information, that what's going on in the world around the neuron as well. And these are really, really important structures if you think of the function of the neuron. And we're going to give a name to these structures. These are going to be our dendrites. So dendrites collect information from around the neuron, and this information then gets carried to the cell body where multiple signals from multiple dendrites can be kind of analyzed, and we can do a summation that is this signal enough to trigger for a nerve cell to have a response, or is it not enough to trigger for a nerve cell to have a response. But dendrites were these structures that were collecting information. And from the nerve cell's body, we're going to see this long tube, this long cord coming out. And again, I know that my tools here are acting up a little bit, but let's see if we can sketch out that long tube that I keep mentioning. And this is going to be known as our axon. And that's exactly what I showed on the previous picture as this structure where we could stick in an electrode and measure the electrical charges within the axon. So that's what we're seeing here, this long axon coming out of the neuron or out of the nerve cell. So that's what's going on here. I don't know why my tools are so overly sensitive that they're capturing those additional lines, but we can clear them away. So let's label our axon to this diagram as well. And what axon does, it carries electrical impulses away from the cell body of a neuron. And what's interesting with the axon is that these messages only travel to one direction of the cell body. So they don't travel to the other direction. So they only travel away from the cell body, as we're seeing here. Sometimes one of the things that we see with some neurons, not with all, but with some, is that we can also have branches from the axon that come out. So let's add a branch here. So the axon can actually divide into branches that carry messages elsewhere to other than just one part. And these branches would be known as our collateral branches of the axon. So let's add that there as well. And not all neurons will have collateral branches, but some do. And if they do have those collateral branches, these collateral branches as well carry the message to one direction and one direction only. So the messages are very, very clearly controlled where they go. Another thing that we see with neurons a lot of the time is that this axon might be actually surrounded by these little blobs of what is almost like this fatty material. So it surrounds the axon and wraps around the axon. So let's add a couple of those blobs of this kind of a fatty material that we're seeing around the axon. Not all axons will be covered with this, but some are and many are. So let's add those there. Oh my goodness, my tools are definitely picking up interference. So I think we have a good amount of these fatty blobs around the axon. And let's just tidy our picture a little bit again. I apologize for the computer deciding to be so sensitive there. Whatever I wipe away by accident, we can add it to this diagram. So let's finish off that loop and let's finish off this loop. So these little blobs of fatty material around the axon are actually known as our myelin. And often my students ask, why on earth would you have these myelin blobs around the axon? And that's a very good question. And there's few different reasons. One way to think about is this, that this myelin kind of provides a little bit of insulation. That's one way to think about, like if you think of that analog of the electric wires and around them, we tend to have a plastic. But probably even more importantly, what these myelin blobs do, they actually speed up the propagation of message along the axon. So normally the message would have to travel along the axon throughout this entire length. I'm going to take away that. I was going to draw an arrow, but I'm getting so much interference there. But if you have myelin around the axon, the message actually gets to jump over that entire portion of axon that's inside this myelin blob. So myelin around the axon actually speeds up the propagation of the message within a neuron. So it kind of gives us a shortcut in a sense that that message doesn't have to do every single step along that axon on that part that's inside the myelin. The message just jumps from one place to another. So we're able to speed up the passage of the message. And let's add one more part to our diagram of a neuron. I want to add our end of a neuron here. So neurons have many different kinds of ends, and we'll get to see some of them today. But at the very end of a neuron, there's an adaptation that's kind of preparing to pass the message onwards, whether it's to another neuron, so forming kind of a set of interlinked structures, or whether it's, for example, to an effector organ. This part is known as our axon terminal. So where does the axon end? It ends up at the axon terminal. And we'll get to see one adaptation that I've kind of suggested on here, which would be synapses, a little later today. If you really like this drawing, but kind of feel that colors are your way to learn, you can totally color it in. I'm just using a yellow color for the most important parts when it comes to the parts of the neuron cell itself. So I'm coloring in the cell body. Again, I'm getting a lot of interference, so let's see how our final drawing ends up being, if there's anything left once I remove this noise. But we're seeing that that was our cell body, and from the cell body we also had these dendrites that came out, and these dendrites were collecting information from the external world. So that was our neuron, our nerve cell. And from the neuron, from the nerve cells, cell body, the message traveled along the axon. So I'm just coloring in the axon, and it traveled to the axon terminal. An axon terminal might have specific adaptations to ensure that the message then how it gets passed to the next structure. And again, we'll get to talk a little bit more about that in later part of our time together today. What else? I did have this branch, the collateral branch, so we could color that in as well. And we also had these myelin blobs that we saw around the axon. Not all of the axon, but in some of the parts of the axon, we had these myelin blobs. They worked as not only just as insulation, but speeding up the message along the axon so that we could pass that message quicker through this structure, more effectively through this structure. So those were those fatty deposits that served in such a role there. So let's add that to our diagram. And again, I know I had a lot of interference, but let's see if we can tidy up this picture to make it a little bit nicer. So I think we're seeing there nicely most of the structures that I wanted you to see. So that should be pretty good. Let's see if I highlight the accent a little bit more so it doesn't get hidden underneath those myelins around it. So there we have a rather good diagram, a rather good representation of a nerve cell. And let's take our story a little bit further and continue our review of structures. What I wanted to do next was to discuss also about special types of cells that we have that play really important role in helping us to support nervous tissues and nerve tissues. Oftentimes, a lot of our research has focused on these neurons, but it's just as important as appreciating neurons for us to realize that there's these supporting cells, either known as glial cells or neuroglia. Both terms I see being used quite a bit. So let's have a look of different kinds of neuroglia that we have. And I'm going to start with astrocytes. And astrocytes are these small glial cells. You're not probably going to be too surprised when I tell you that the name gives us a clue that they tend to appear as a little bit like these star-shaped structures. Remember, they're small though, small cells that look a little bit like stars. And let's discuss these astrocytes a little bit more and have a look why we need to learn about them. Why are they important structures for us to be familiar? These astrocytes are really important and involved in metabolic processes and metabolic responses. So metabolism. In addition to that, these astrocytes can actually also produce that myelin that we just saw earlier on around the axons. So those would be some notes to take from about our astrocytes to notice. The next glial cell type that I want to mention, and I have more information about each of these on your full lecture videos, the next one that I want to mention is going to be our oligodendrocytes. So oligodendrocytes, if we look at them, a lot of the time when we're studying them, you will end up noticing that they are associated very closely with the axons. So let's draw an action here, provided that my tools start working. Here's our little section of an axon, and these oligodendrocytes have a tendency that they have their cell body, but this cell body then produces and secretes myelin around the axon of the neuron. So again, let's see if we can tidy up this image. I know it's a little frustrating, all these extra lines that keep appearing. So hopefully our diagram will be a little tidier after removing that. So here we're seeing our oligodendrocyte cell and how it's producing to the around the axon this myelin. So let's add that. I'm gonna cancel that. Oh, I can't cancel it, so let's just redraw that. So there's our action. Around it, we will see the myelin produced by oligodendrocyte. So we can add the same note to our list of notes about oligodendrocytes. So let's remove those. And I think we have a little bit better notes there. The next type of glial cell that I wanted to mention is going to be known as our microglia. And microglia is characterized by being very, very, very small. A lot of the time, people describe this as being kind of a spider-like cell. So it's really, really a tiny cell type that we end up seeing. And let's add a little bit of notes of that as well. So like I said, a small cell type that we're seeing there. What else can we say about a microglia? Let's add these glial cells are often also phagocytotic, so they they dispose materials that we are not wishing to see at the area at the site. So they kind of clean those areas as well. And the final glial cell type that I wanted to add to our notes is going to be called ependyma or ependymal cells. So let's add that to our list. These ependymal cells, they really are often found at the sites where they line different kind of cavities, so forming kind of boundaries in that sense. I think that a good example of that will be around the brain, where we see that ependymal cells form these boundaries, making sure that we're keeping materials that shouldn't be entering from entering to these structures. So let's add that note here. These ependymal cells, as you can tell from the drawing that I just did, are often ciliated. So those little finger-like projections from these cells is one of the things that we'll end up seeing. Let's see if I can add that. Yes, there. We end up finding ependymal cells in places like spinal canal, in ventricles, and also within the brain. So really those many cavities that I mentioned earlier on. So those are going to be the three of our important glial cells that we need to know, the supporting cells that assist our nervous system. So I mentioned earlier on that you can measure membrane potential. And to measure the membrane potential, you stick an electrode inside the axon, but not all the way through. And then the other end, the ground for this measuring apparatus would be outside the electrode. And then you can tell that there's going to be changes in the electrical charges of this neuron as we go on and measure that. So let's have a look at those electrical impulses a little bit. And as we're starting to talk about these electrical charges, one of the things that we'll end up seeing is that the inside of the neuron has a negative charge. It's typically about negative 70 millivolts. And this is established with our sodium-potassium pumps that we find at the surface. So moving these charged particles in and out of the neuron so that we establish that negative charge of negative 70. And I actually have a couple of videos about that on our learning module explaining in more detail how the resting potential of a neuron is accomplished. So normally, nerve cell, when it's at rest, it's going to have a charge inside it that's negative 70 millivolts. Then if a message passes, we're going to see a change into this. But this negative charge was accomplished because for every time that we're pumping in sodium, we're pumping 3 sodiums, we're pumping out 3 sodiums, we're letting in 2 potassiums. So the overall charge inside the cell becomes negative charge. So there's an imbalance, negative charge inside the nerve cell. Then something happens that causes a message to be passed, an action potential to be passed. And in response to that, we have what we know as depolarization. During depolarization, sodium channels open and sodium rushes inside the cell, making the cells inside become less and less negatively charged until it reaches 0 millivolts, and the insides can become even slightly positively charged because of that sodium rush inside the cell. This process is known as depolarization. And let's break apart that word. So polar means that you're far away from two ends. And depolarization means that you're no longer far away from the ends. So we're coming close to 0. And like I said, we can sometimes even shoot a little bit above the 0 because sodium was rushing into the cell. This state will not last long. However, we have to go back to the normal. So the sodium channels close and potassium channels open, and we start to neutralize the charges within the nerve cell, and the membrane returns to its resting potential. So this movement back towards that resting state of negative 70 millivolts is known as repolarization. So we're going back to polarized state, far away from 0. Oftentimes we end up actually going further below the negative 70. This is known as undershoot or hyperpolarization. This hyperpolarization really gives us a kind of a recovery period during which another action potential cannot pass. So we create this space for these electrical messages that are traveling through the neuron so that we have time to recover before another action potential can take place. So, like I said earlier on, I'm just gonna see the concept I think we already discussed about the action potential. Action potential typically propagated one direction only, away from the cell body towards action terminal, and it passed along the axon. Here we're seeing kind of enlargement of this part of the axon. In non-myelinated axons, the message just passes as these many little steps that follow each other at different parts of the axon. We were just looking at one individual spot when we drew that graph just a moment ago. However, if we had myelin around the axon, this caused, first of all, it kind of supports this action. It also insulates this action, and it speeds up the propagation of the action potential. So the action potential could jump from one myelin gap to the next. So we're getting faster propagation of the message. And the very last thing that we have to look at before we wrap up for today is to look at the structure known as synapses. So we're now looking of that axon terminal. We're seeing the axon terminal coming in here, provided that this decides to start working. And this action terminal actually typically has a little bit of an enlargement or adaptation there at the very end. And this is going to be important in a little bit. We'll see why. If we get this structure drawn without too much interference. So that's our axon terminal from the first cell that we'll be looking at. The rest of the cell is outside from the view at the top of the screen, so that's why we're not seeing it, but we're seeing only the action terminal portion here. So we often call this part, we call this as our presynaptic cell. And with that, we're referring to the fact that this is the part before we get to the synapses proper. So that's our presynaptic cell. And what we're seeing with the presynaptic cell is that the message is now coming, traveling down the axon as we saw before. And once it reaches this axon terminal, what tends to happen is that this causes vesicles that we find inside here to move and to be releasing their contents to the end of the axon. So we're releasing what is known as neurotransmitters into this space. So these are chemicals that help us to pass message. And notice how the message is not now passed as an electrical impulse, but it's rather passed as a chemical signal. So this action potential causes the release of the contents of one of these vesicles into this synaptic space that we're seeing here at the axon terminal. Then we're going to have a second structure, and let's say that this is a neuron for the sake of completedness, but it could be another structure as well. It could be a muscle. We talked about neuromuscular junctions, but we're seeing a second structure on the other side here. And let's see if we can remove those lines. This is going to be known as our postsynaptic neuron. So if that's our pre and postsynaptic neurons, we're also going to have a structure known as synapses in between those. So synapses is this little gap between these two nerve cells. On the surface of the postsynaptic cell, we're actually going to have receptors for those particular neurotransmitters that were released earlier on. So we have receptors for those, and these neurotransmitters will then bind into these receptors. And as they bind into these receptors, then they trigger changes inside this second cell, causing a message to be passed onwards. And continuing within the nerve cell. And let's see again if we can tidy that picture a little bit. You could, if you were very eager, do a little bit more of illustrations to this, color these structures we saw earlier on. Our action, we colored it with yellow, but just because I'm having such a hard time with my computer being so overly sensitive, I think I'm not gonna fight too much with the coloring today, but you could do your own, you could do whatever works for you to symbolize these structures so that it's easier for you to follow along if you're a very visual learner. So we're seeing that we had the presynaptic and postsynaptic cell, and then we had those vesicles within the presynaptic cell that contained those neurotransmitters that we talked about. So you could as well mark those. And the contents of those vesicles which traveled in this synaptic gap. And finally, we had receptors for those particular neurotransmitters that we had there. I think that that shall do. That's a pretty good explanation of a synapsis. And we can actually take this a little bit further and have a look of a real world example of what a synapsis really looks like. So we're seeing the presynaptic part, we're seeing postsynaptic part. There would be a small gap in between. So messages actually travel in the nerve system, not just as an electrical signal, but also as a chemical signal between these small gaps between the pre and postsynaptic structures. So we're seeing those same structures that we talked about before. If you're interested about synapses, I have a little bit more information here to show you. This is really passing messages from one neuron to the next neuron, or from a neuron to an effector cell, like we saw in a neuromuscular junction. I think we spoke about that earlier in our previous chapters when we talked about the muscular system. We also had a chance to do a simplified diagram of this chemical propagation of the messages within the synapses, how signal traveled that caused the contents of the vesicles, those neurotransmitters, to be released into the synaptic gap, and there they create a change in the postsynaptic cell. Having said all that, I think we have came to the end of everything that I had planned to cover today. And I know that it's been a little longer session, so I think it's a good time for us to wrap up. So for the interest of time, I'm not probably going to go through the homework questions for this chapter. If someone's really has a burning desire to have a look of those, you can let me know and I can do a quick video showing a couple of examples, but the format follows what you've seen in the previous chapters, so nothing new there. Again, thank you for anyone who joined me for this recording of this session. I really appreciate it, and I look forward to another great week of learning with you. Have a good week, and remember, I'm here to help, so let me know if there's anything at all that I can do to make your studying easier.